let's start about a very basic question. Can you tell us what are you working on and what does it matter?
Sure. I mean, we're working on many technologies which are at the frontiers of science.
Yeah.
And the idea is to focus on topics which are too risky or too long term for the private sector.
Mm-hmm.
And the one point I wanted to talk to you about was the fusion technology. But happy to talk about many other topics we're working. We're working on things on antimicrobial resistance. We're talking about space observation. We're talking about carbon capture in soils. So many topics. 4 big missions: education, climate, how life sciences, and what we call human-centric digital.
Okay, great. And how did you actually started to do Jedi? Can you actually maybe highlight also all maybe the political ecosystem that triggered this
Sure.
and
I mean,
the scientific level.
I don't know those who are in the room. Are you European, coming from the US? Where are you from?
Europe. Yeah.
Europe? From where?
And Romain, Europe as well.
French.
Yeah.
French?
Estonia.
Estonia?
Greece.
Greece. Okay, so we have a perfect combination: east and west, north and south. I mean, the perception we all have, especially since the Corona crisis, is that there's an acceleration in science and technology. That there is not necessarily growing, but there is a huge part of the population which I think, for good reasons, is not trusting science. It's very interesting when you look at science fiction, for those who read either comics or science fiction writings. 20 or 30 years ago, science fiction was very often utopian. Mm-hmm. That means the future was these flying cars, and when you look at these 50s or 60s comics, it was rather positive, and it turned in the 80s and 90s very dystopian. And so today you have rarely science fiction. So the question is, how do we see the future? How do we project ourselves for our children, for society, etc.? And the whole idea of Jedi is to say that during that time, the Europeans in particular seem to be not necessarily at the forefront of events. They seem to be increasingly shaped by what is happening. The pandemic was something which is absolutely not a black swan. Black swan meaning something which was not planned. I mean, people have been talking for pandemics and we've lived pandemics since humanity exists. And we knew that with globalization, connections through planes, trains, etc., and communication nodes, when a pandemic would happen, it would be much worse than everything we knew in the past. But we have this difficulty of planning ahead, and I think it's beyond science. It's a democratic issue. Is actually you realize that free societies or democracies are actually those who are today the more short-term in their approach. And the wrong approach would be obviously to say, look at the authoritarian systems. They are the ones who have plans for, think about China, plan for 2049. Obviously, the wrong answer is to say we need to adopt these systems. The question is, how do we build long-term thinking? This whole idea of Jedi is to say, increasingly when there is science and technology involved, how do you ensure that you are not caught by surprise, but that you are kind of planning ahead? For those who have read Bertolt Brecht's, there's no German in the room. Galilei, it's an old story. You know, when Galilei discovered that the sun, it was not the Earth anymore, the center of the universe, which was basically the construct around which the church was built, but it was the sun. He had two choices: either disclose it and actually make the whole universe of most of people kind of crumble, and also, and that's why he got under big pressure and from the church. But or you don't disclose it. Closer to us, some of you may know when Albert Einstein, who was obviously one of the founders of nuclear physics, discovered the power of the bomb. There was this famous letter that he wrote to Roosevelt in 1943, saying, be careful, there is obviously a commercial or a civilian usage because it can create an immense amount of energy, but it can also be used to release horrific amounts of destruction. And so the question is, are you just letting others with necessarily values which are less humanistic or less or are you trying to be ahead and try to control things as much as you can? And nuclear was always like that. I mean, it's the weapon of mass destruction by definition. And that's why I'm very focused on this nuclear fusion, because in this energy crisis that we're all experiencing, there is this kind of hope that we could reach what is basically our basic energy since ever, because the energy we are living on is the energy of the sun. And in the sun, you have this nuclear fusion, which naturally occurs. So happy to dive into that.
Yes.
So, but this whole idea of Jedi is to say, let's not do technology for technology, which sometimes you see in some environments. I don't want to, oversimplify, but you can see that sometimes in some in some environments, a lot in the US. You can see a lot that China has been using technology massively in the last, especially 2-3 years, to become the ultimate control state. I mean, people wonder why zero COVID, why is China still using that and kind of crippling their economy, making this their citizens. But actually, with zero COVID, you are basically, I lived in China for 10 years now, you actually are living on the rhythm of being green, orange, or red. Green meaning you can buy you can go in stores, you can travel. Orange means you're confined at home, and red, you need to go to one of these quarantine camps. And that is something that you check 10 times, 20 times a day. That's one. And secondly, they use now social media to basically micro-poll all the time, being able to identify the little source of frustration. I mean, this is obviously horrific, because even George Orwell, I think, didn't expect that you could use so much things with digital and things. So the question is, what do we want in Europe? Do we want to be shaped by events? A little known fact, but face recognition, which a lot of us have doubts about or suspicion about, is happening everywhere, and we will have the Olympic Games in France. The political pressure will be too big to put cameras everywhere, obviously. On the other side, do we want to have systems which are centralized with all the risk of being hacked involuntarily, or hacked or used? Unfortunately, today, 97% of all the systems in France, I'm not talking about China, are of Chinese origin. So if you are in Roubaix, you have 400 cameras who are following you and tracking you. And the mayor got an offer. You remember the Godfather, an offer he cannot refuse, because basically Hikvision, which is the provider of that, came to the mayor and said, I'm going to help you solve your problems of crime and of even of circulation. I'm going to bring you. For the company, it was very good, because basically they're also improving your face recognition algorithms freely. So, old story. If you don't pay for it, you are the product, and that's what's happening.
Okay, and can you talk more about nuclear fusion, right? And what is do you already have a roadmap of development?
I mean, you remember Stefan Zweig's book about Brazil? It's there's no Brazilian in the room, so I can hopefully there is no. He used to say it's the country of the future, and it will always remain. The joke was it will always remain like that. Unfortunately, what happened in the last couple of years was a bit showing that it was true. And fusion was the same. The joke was it's the ultimate source of energy for the next 30 years, and it will always be in 30 years, meaning it's a generation ahead. What is interesting is that I mean, just to give some very basic concepts, how fusion works in the sun. I mean, often people don't really. Some very basic thing. The fact that it's that it's a star with so much gravity makes that the gravity itself creates so much pressure that you have actually a third state of matter. You have solid, you have liquid, you have gas, and you have a fourth state of matter, which is called plasma. And when you have this plasma state, which depends on the density, but we're talking about 10, 15 million degrees, so hot. Then you have a merging of atoms, and merging of atoms is a bit counterintuitive. Actually, releases much more energy than when you split atoms, which we know in fission, which is nuclear reactors or atomic bombs, in an order of 4 or 5 times more for the same mass. And the interesting thing with fusion, and I'm not a techno optimist, but is that it's the state in which it happens is so unstable that as soon there's something which gets disrupted, the reaction stops. So there's not what is actually, and in France currently there's a huge debate, in Germany there's a huge debate about nuclear energy. Should we reopen nuclear plants because of the energy crisis in which we are? But when I see what is here, I think here in this chateau there will not be an energy crisis because it seems to be very comfy, etc. But actually, a nuclear fission, without being pro or against, it's basically a controlled bomb. I mean, you're permanently stopping what is called the chain reaction.
And you don't.
But and we saw that yes, most of the cases it works well, but there are cases where either you have an uncontrolled reaction or what we call a meltdown, which happened in Fukushima. For fusion, it's different. First, you use elements which are very, very common because it's basically isotopes of hydrogen, which are found in salt water, so in oceans, very relatively easily. It releases only water, so there's no carbon emission, obviously something interesting. There is this instability which makes not normally, there is no risk of something which gets uncontrolled. And last but not least, it is not what we sometimes hear that it doesn't produce. It produces nuclear waste, radioactive waste, but I don't know if it's better, but the nuclear waste you produce in nuclear plants is there for 10,000 years, especially the plutonium can be then used in bombs. In the case of fusion, you produce nuclear waste, which is only, if I may say like that, radioactive for 50 or 100 years. But it's not this kind of things. There's a location actually not very far from here in France where they are thinking about putting the ultimate waste, the one which will be, and it's very interesting because in a way because we need to define a place where you're going to put things where people are going to speak a different language, where obviously there's going to be a different civilization in 10,000 years. So you need to tell people who are going to live on this planet, if there's still somebody there, in 10,000 years, that there are things which are super dangerous. So you have linguists who are inventing. It reminds a little bit of if you remember the Voyager probes that were sent in 78 and 79, where we tried to explain people who could read that, where is the Earth, who are we? So you had these very relatively simplistic images of men and of a man and a woman, the position of Earth, the position of our star in the galaxy, etc. Very interesting. Anyway, so you don't have that, and but in order to get that is an old and today an unresolved physical issue. If I can dwell on that 1 minute, basically there are two ways to achieve a fusion. So you need to create huge temperature and density. You achieve that today in two ways, either by compressing, but not physically, by magnetic fields. So you compress matter so much that the density increases, the temperature increases. Since you don't have the density of the sun needs 15 million degrees. If you do that without the density of the sun, you need 150 million degrees. So it's literally, and then the problem is you have no container. How do you keep that? So one is magnetic fields. The second one is using lasers that basically bombard very, very small atoms, because you need very, very little matter from all directions, and you overheat them. So that's the two ways to achieve it. And the main issue today, which is not completely solved, is how then you contain this sun in a bottle, because obviously there's no container who can keep it. And the solution, which is an old solution, it's from the 50s, is to contain that in magnetic fields, because this plasma, this matter, is actually not a matter which is stable, it's a matter which is ionized. Without getting too technical here, ionized means that it's charged, it's plus or minus basically. So that means that with a magnetic field you can basically keep this matter. Problem is, if you have a magnetic field, if you do it linear, you will have ends where the plasma will end. And therefore, today, most of the fusion test reactors are this kind of donut shaped, which people call tokamak. You have one which is in Oxfordshire. You have a very, very big project being built in France, which is an international program with 35 countries called ITER. ITER is the way in Latin. It's International Test Experimental Reactor. And now you have a lot of startups emerging in that field. Very heavily concentrated in the US. To my latest count, I think there were 26 startups in the US, 4 in the UK, 1 in Germany, and 2 in Japan. And they try different ways. They try to miniaturize because these tokamaks are huge. I mean, the plant which is being built in near Cadarache,
the donuts, you mean?
The famous donuts, they're gigantic because you basically need to create electromagnetic fields which are 100,000, 10,000 times more powerful than, for example, the magnetic field of the Earth. So you need, how do you create a magnetic field? You need these gigantic, bobine, rolls. So you have a huge innovation going there. You have a huge innovation about how to reach the confinement of the chamber. Interestingly, something very similar to what we had in Corona. If you remember, one of the main issues of the vaccines were that you needed to have the vaccine stored at -60 or -70 degrees, which made it very difficult to have also vaccines go to the global south, etc. But still, you use for that helium, which you find in hospitals, etc. That until a couple of years ago, most of these ultra high magnets could only be reached with temperature close to the absolute zero, which is -250 degrees, which is extremely difficult to achieve. Now there was a breakthrough a year ago by a team by the MIT, which achieved superconductivity in these magnetic fields with -80. So that's huge. The same team was also able to miniaturize by a factor of 20 or 40. And it's a little bit like in a plane. The more you reduce weight from a plane, it actually has a double effect because you need also less weight to be carried to carry the fuel. So it's the same thing. When you can miniaturize, it's not just a linear, it's really an exponential approach. Then you have still a lot of issues. And today you have even a societal issue is you basically have a race between, okay, why should we put efforts in fusion? Why we have so much progress happening at the same time with renewables? So it's basically an equation with many unknowns. But it's a fascinating field in material science, in understanding also how our stars are working. Exciting. Yeah.
And what is why do we don't have enough, I guess we don't have enough startup, right, in Europe? Is JEDI having a program to accelerate the creation of those startups in Europe?
We don't invest. What we do is we fund research projects. But
that might be interesting.
Yeah, I don't know. Maybe that we should have started just to understand who is in the room. Maybe I'm talking to people who have absolutely no interest or clue about what I'm talking about. In which field are you? Or
I'm in space as well.
Okay.
As well. Actually, what was except for
yeah, I will be forced.
Okay. So you all three are in the space area, and in which field of space?
robotic missions.
Okay.
Satellites.
Yeah, space engineering.
Okay. Would love to know what you think about a new constellation that was announced 2-3 days ago. Okay, good. So, is there, by the way, anybody who is thinking about nuclear propulsion for space, or is it there's nothing happening on that aspect?
You mean fusion for propulsion?
Yeah, fusion or fission. The Russians used to do that with their very first. The Russians, the Soviets. So I have to include our Estonian friends, and that past, that far past. But I think one of the it's still was Estonia one of the hubs for the space program of the Soviets, or not at all? No, there's no relationship.
In the Soviet Union, you mean?
Yeah, in the Soviet Union.
I don't think so. Maybe.
Because Ukraine was
Yeah.
was a huge.
So,
Yeah, my view with fusion for propulsion is wait for fusion to become a reality, and then try to launch it into space and think about these things. But it's really apparently you can use it to reach percentages of light velocity with it. So it can be really powerful even for interstellar travel.
Yeah, absolutely. It's probably the only way for at this stage. I mean, until we get teleported, but that's another. I didn't bring my little teleport me, I think. Okay. Okay.
What I'm interested in, and maybe I think here into Eric's field a bit, is you have fusion as, let's say, in quotes, a miracle solution to the energy problems. And you have other, and again in quotes, miracle solution, which is space-based solar power, which I'm interested in. And there's some kind, both have their uncertainties, different types of uncertainties, let's say. And I'm interested into studying, what is the trade-off between those in the long term. Maybe one doesn't work, maybe one never becomes competitive, maybe one takes over completely, and then you have this miracle solution really, and you need nothing else. Maybe there's a mix where both are viable there. So I think that's an interesting question. And do you have something?
You have heard about the Solaris project that was just announced. I don't know how much this is a paper project from ESA or how much is reality. Okay, but I think it's more an announcement. But I think that look at what's going on right now. We realize that yes, it has some kind of a miracle part. First, fuel is available, no carbon emissions. Apparently, there's a roadmap to miniaturize that, so make it more efficient. Yeah, I forgot to say for a long time, the reason fusion did not work is that the amount of energy you needed to, it's called the G, I think, was negative because you needed more energy to heat up the plasma than the energy that you can get released. So it's that's why it was considered as almost a big question mark, even from a physical standpoint. Apparently, with miniaturization, you get to positive. There's a US startup which is very hyped right now, which is called the Commonwealth Fusion Systems, CFS, which is announcing a positive G, that means more power out than in, for 2025. So we're not talking anymore. ITER, the project in France, is supposed to do its first positive fusion in 2035. So you see, it's still. But on the thing, look at what's going on. I think we realize that actually a mix is what will combine the different conditions, which is first you need energy 24/7, which you don't have with renewables, obviously. Secondly, you need energy that you can ramp up in case you have a disruption. Think about that. Things which were considered as impossible, like disruption in infrastructure, is now completely possible. So if you don't have backup, today backups is a smart thing to do. And three, then you have a combination. Currently, for example, hydrogen, which is considered as potentially a way to store energy, which is a bit the missing link, is only is produced by renewables, but it can also be produced by nuclear, because you need a lot of energy to transform, to create hydrogen if you don't want to use the traditional means, which are very much carbon emission. So when you think about this, one other thing I looked a little bit at different projects doing, like, you basically take this energy from the sun and then you redirect it basically through concentrators, etc. What will you do? Will you then do a huge steam engine? Can you maybe use it to actually heat up with concentrated lasers the famous plasma? So I see more complementarity. And what is also interesting, and that is what we at JEDI are super focused on, is we believe that today the real disruptions, I don't know how you're building up your teams, are coming not from having 20 rocket scientists in one room, that you are pretty linear in your approach. And we saw that I'm a big fan
Yeah.
of Europe, but we saw that in the European Space Program, where until 2 or 3 years ago, we had many people had difficulties to just imagine reusable rockets, which is not rocket science by definition. So I think it's going to be at the combination of material science, of people working on high-powered lasers, people who are going to work on magnetic fields, and that's interesting. And I think all of our job, and I think that's why I'm also very interested in this kind of. I'm discovering. Hello.